All right, so welcome back to the next class in mechanics, which is mechanics of the ideal fluids and viscosity. As you understand that we have covered another chapter, which is surface tension already, and we dealt with surface energy, surface tension, and angle of contact, excess pressure on curved surfaces, capillary rise, equilibrium, vapor pressure over curved surfaces, some of that, some numerical problems on that. And we need to understand now some of this from the concept of the ideal fluids and viscosity. So to understand that, we need an understanding about what is a Newtonian and non-Newtonian fluid, streamline and turbulent flows, Stokes law for terminal velocity, equation of continuity, Euler equation of motion, streamline motion, and Bernoulli's equation and some of its applications. In simple, the mass density is given by rho is nothing. It's like specific gravity, which is the ratio of density of an object or a substance with respect to water. Whereas mass density is given by delta m by delta v, whereas if you have any substance like solid, liquid, or gas of mass m occupied a volume of delta v, then basically that is delta m by delta v is the mass density. And in many of the cases, this is what will be used in this chapter for mathematical and numerical calculations. Now, pressure is another concept that we need to understand before we get into this course. So pressure is largely generated because of collisions of particle, molecular atom within a gas or liquid generate a force against the surface that is in contact with it. So in standard air, what happens is you have nitrogen, oxygen, water, and some other molecules involved, with most of them having a typical speed of 450 meters per second, which is a lot. And they travel and they collide with each other a lot of times. And in 1 square inch of any area, maybe your skin, it hits almost 6 billion times. That gives rise to the air pressure that we generally talk about. So any small section of the wall in a container with air or liquid particle colliding with outside the, so it basically transfer the momentum. So as these particles actually collide with the wall or the particular area that you're measuring the pressure in, so it is transferring its kinetic energy into that. And that leads to a force. And if you divide it by the area, so force per unit area gives you the pressure. Now, clearly the hydrostatic pressure and gravity, these kind of equations you must have studied in your higher secondary courses. And largely gravity is the ultimate cause for hydrostatic pressure. Hydrostatic pressure refers to non-accelerating fluids, particularly fluids at rest. So at distance h below the surface of liquid with a density rho, the pressure is increased from the pressure value by an amount, rho gh. What we measure at atmospheric pressure is merely the weight per unit area of the column of the atmosphere extending upwards from the Earth's surface. It is often quoted in terms of equivalent weight column of mercury. Pascal's principle is another you probably have heard about, and that is largely used in hydraulic equipments like hydraulic press, and that's something that has the power to actually pull a car even. An external pressure applied to a fluid within a closed container is transmitted undiminished throughout the entire fluid, which means like if you have a pressure, if you have a container and a fluid within a container and you apply some kind of external pressure within it, then this pressure is transmitted without any change. Undiminished means without reducing or without a change throughout the entire fluid. The interesting principle is Archimedes' principle. Objects measured in a fluid at rest experience a buoyant force, Fb, directed against the gravity, with the magnitude equal to the weight of the fluid displaced by the object. So what it means is any object, if you dip it in any fluid, say water, it will feel some kind of a resistive force against the gravity. And the magnitude of this force is basically the weight of the fluid displaced by the object. So if the object has a volume something, then basically the amount of weight of fluid that it will displace is the volume into the gravity, like its density, and that's basically the force that it will feel. Now we come to some aspects related to this chapter currently we are studying, and we need to understand what is ideal fluid. So any ideal fluid, when steady, the velocity, density, pressure will not change in time. There will not be any turbulence. It's incompressible. So it's steady, it's incompressible. The density is always constant. It's non-viscous, no external friction between adjacent layers. So viscosity concept comes from this one, that ideal fluid is non-viscous. So between layer to layer, there will not be any friction. So when there is some friction between layer to layer, or there's some force, that's basically viscosity. A rotational, no particle rotation about center of mass. That gives the concept of Newtonian fluid and non-Newtonian fluid actually. A Newtonian fluid's viscosity remains constant no matter the amount of shear applied or the constant temperature. These fluids have a linear relationship between viscosity and shear stress. What is a non-Newtonian fluid? You probably guessed that non-Newtonian fluids are the opposite of Newtonian fluids. When shear is applied to a non-Newtonian fluid, the viscosity of the fluid changes. The behavior of the fluid can be described in any of these various ways, but basically what you have to understand that in non-Newtonian fluid, the viscosity of the fluid will change. Now, we definitely need to define viscosity. So far, we have considered only ideal liquids, liquids that can flow without any resistance. Now, real liquids have a property called viscosity, which is tendency for the liquids to resist flowing. For example, if you have a syrup that flows more slowly than water, we say that the syrup is more viscous than water. Ketchups and some other also examples are there which are viscous. And viscosity is sometimes referred to as the thickness of a liquid. Viscosity is important property for motor oils. In terms of definition, viscosity is the quantity that describes a fluid's resistance to flow. Fluids resist the relative motion of immeasured objects through them as well as to the motion of the layers with differing viscosity within them. So in general, if you have from layer to layer of, of the same liquid, if you have like while in motion, different layers of a liquid actually has some kind of friction or force between them, that is basically the viscosity. So it's basically the ratio of the shearing stress, that is F by A, to the velocity gradient, which could be delta x by delta z or delta vx dvx by dz. So viscosity can be given by shear stress by velocity gradient. The more usual form of this relationship, called Newtonian equation, states that the resultant shear of the fluid is directly proportional to the force applied and inversely proportional to its viscosity. Similarly to the Newton's second law of force, it can be apparent. Now, viscosity can be measured by dropping a ball bearing. One of this experiment may be in your BSc courses. The one with the lowest viscosity will actually create less friction or less resistance against the ball, the bearing falling. So it will fall fast. A highly viscous liquid will create more resistance, and that is why the relative speed will actually, the effective speed velocity actually will be lower and it will fall slowly. This also affects the flow or the flow conditions in liquid. The laminar flow is the one where the flow is streamlined. Generally, fluids at a low speed, whereas turbulent flow is random, irreproducible, generally the fluids at a high speed. In streamline, the path of the particles in different points, the tangential to that, whereas there is generally no crossing of these streamlines. There are other ways of actually defining streamline, laminar, or turbulent flow. Streamline flow of a liquid is that the flow in which each element of the liquid passing through a point travels along the same path and with the same velocity as preceding element possesses through that point. So basically, B point at A, B, C, the V1, V2, P3, they will be mostly same. In a laminar flow, if the liquid is flowing over a horizontal surface with steady flow and moves in a form of a layer or different velocities which do not mix with each other, The flow of the liquid is called laminar flow. Maybe when you consider flowing of liquid in a table on the table, something like a flat surface. Turbulent flow is when a liquid moves with the velocity greater than its critical velocity. That is important term, critical velocity. So whenever the fluid is flowing above the critical velocity, which is defined by its viscosity, the motion of the particles of the liquid becomes disordered or irregular. And this motion is called turbulent. In this kind of flow, the path of the velocity of the particles of the liquid change continuously and hazardously with the point to point. Most of the external energy maintaining the flow is spent in producing this turbulence within the liquid, and only a small fraction of the energy is available to the forward flow. These ADs are seen by the sides of the pillar of the river bridge. For mathematical calculation, you will also have to understand the mass flow. So if you have a point A and point B, then the mass flow within that will be rho 1 A. Rho 1 is the density, A1 is the area, V1 is the velocity, and delta T is the time. So the mass flow will be delta M by delta T, delta M1 by delta T1 in this case, which is rho 1, A1, and V1. The reason to bring in this concept is to introduce the conservation of mass. So if we do not have a source or sink, which is drains, then generally the mass is constant. So the rho 1, A1, B1 and rho 2, B2, A2 and V2 is constant in the image in the last slide. So in case of an incompressible liquid, where rho 1 and rho 2 are same, the density remains same. It is A1 V1 is equal to A2 V2, and that remains constant, which means the narrower tube and larger speed becomes faster. So the moment you narrow the tube, the fluid speed will become larger, it will become faster. Whereas if you have a wider tube, because of this mass conservation, the speed will be reduced, it will become slower. That's basically the equation of continuity. It's something that will be introduced to you in a later stage in electromagnetic courses in the conservation of charge. Now that automatically is visible from this image, that is what accelerates the fluid. As we discussed, the difference of pressure between these 2 points, which is P1 and P2, is largely the cause of the acceleration. And that's the Bernoulli's principle. So Bernoulli's principle comes from the conservation of energy. So if you have a concept like this, an image like this, whereas the two ends of this funnel, this pipe, will have a pressure of P1 and P2, area of A1 and A2, and a height of Y2 and Y1. As we understand, because of the conservation of energy, for steady and incompressible liquid, non-viscous, irrotational. Because of the Bernoulli's equation, the kinetic energy, potential energy, and the external work all needs to be accounted together. And that gives you the final result, which is P plus half rho V square plus rho Gy is constant, whether it's the point in either of the side. So basically the pressure plus the kinetic energy, which is half rho V square, the static energy, which is rho Gy, remains constant. It can be said also, just the same definition, that Bernoulli's equation comes from the conservation of energy. Flow in an ideal fluid conserves total energy. When the fluid flows in a gravitational field, the energy per unit volume of the fluid comes in three forms: the gravitational potential energy, which is rho Gy, the kinetic energy density, which is rho V squared by T, and the internal energy density, which is the P. The requirement that the total energy be conserved implies that the sum of these three forms remains constant throughout the flow. And that's the Bernoulli's principle that is given by this equation. So this we can use to measure pressure. And as we mentioned that mercury barometers are used to actually measure pressure, particularly the atmospheric pressure. And that can be given by the height in a location. The height of the mercury in the tube gives you directly the pressure in that area. If you know the rho and the G, rho is the density and G is the gravitational constant. You can also relate that most of the disordered motion in liquid comes because of high pressure and low velocity, whereas the ordered motion comes for low pressure and high velocity. Take another example of a U-tube manometer. The vectorimeter, here the speed changes as the diameter changes and can be used to measure the speed of a fluid flow. Another example is the pitot tube. Some further concepts that we don't want to skip before we end are Euler's law of motion. In classical mechanics, Euler's law of motion are equations of motion which extend Newton's law of motion for the point particle to rigid body motion, formulated by Leonhard Euler. Now, Euler's first law states that the linear momentum of a body is equal to the product of mass of the body and the velocity of the center of mass. So internal forces between the particle that makes up a body do not contribute changing the total momentum of the body, and there is an equal and opposite force resulting in no net effect. This law stated as this. The second law states that the rate of change of angular momentum about the point that is fixed in an inertial reference frame, often the mass of the body, is equal to the sum of the external moment of a force, the torques acting on the body M, about that point. So the external moment of force, the torque, which is M, is given by dl by dt, which is the rate of change of angular momentum. Stroke law is another concept, which is the mathematical equation that expresses the settling velocities of small spherical particle in a fluid medium. The law is derived considering the forces acting on a particular particle as it sinks through the liquid column under the influence of gravity. The force that retards the sphere moving through the viscous fluid is directly proportional to the velocity and the radius of the sphere. And it can be expressed as this. So you basically have practical of this kind of formula, particularly the Stokes law, where the force is actually given by 6 pi eta r and v. Now the terminal velocity is also another concept which deals with raindrop. Initially, due to the gravity, it accelerates. And the velocity increases, the retarding forces also increases. And finally, when the viscous force and the buoyant force is equal to the force due to gravity, the net force becomes zero, and so does the acceleration. The raindrop falls with a constant velocity. Thus, in equilibrium, the terminal velocity Vt can be given by this formula. When rho and psi is the mass densities of the sphere and the fluid respectively. And from this one, the terminal velocity depends on the square of the radius of the sphere and inversely proportional to the velocity of the medium. Reynolds number is another concept that you will probably need for your practical. Reynolds number is a dimensionless value which is applied in fluid mechanics to represent whether the fluid flow in a duct or a pad, a body, is steady or turbulent. This value is obtained by comparing the inertial force with the viscous force. So the Reynolds number is denoted by Re and can be given by the ratio of the inertial force by the viscous force, and is used to determine the velocity, diameter, and viscosity of the fluid. So in general, if you have a number less than 2000, it's called laminar. More than 4000, it's called turbulent. Between this is basically a transition.